Hey, hello everyone. Thanks for coming. I've got the pleasure to welcome Dr. Simon Hain, to give us a talk today. So he's currently based in ANU, where he did his PhD, where he's been previously been up at UQ and over in England at University of Sussex, I think it was. So he's always been focusing on quantum sensing in various different forms, and specifically for this one, looking at whether we can evidence quantum gravity, excitingly. So it would be good to hear him talk. I mean, it's been a while since I've heard him give a talk. I think the last time was when you were giving me teach me undergrad quantum physics. So it'd be nice to hear what you got to say. I think we're all very excited. So take it away, Simon.
Thanks, Ryan. Okay, thanks everyone for inviting me here. I'll just share my screen and then make that big. Yes, and move this out of the way. Great, yeah. This is a real pleasure to be invited to this. This is a topic that I am only just sort of recently getting into, and I see there's a very active community here doing a lot of really exciting work that's inspired me a lot. So yeah, I'm just keen to be a small part of it. Okay, so the outline of this talk is really the possibility of testing quantum gravity with ultracold atoms. So really, I'll just break this down into a series of questions. Why do we want to test quantum gravity? How do we test quantum gravity? Why would we want to test it with atoms? Well, the spoiler alert there is, if all you have is a hammer, you start to see everything as a nail. How do we test it with cold atoms? And in particular, will it work? Okay, so this is the Einstein's field equation. On the right-hand side, we have the stress energy tensor, which tells us how matter is distributed. And on the left, we have the Einstein tensor, which tells us how space-time curves. And I think we're all probably familiar with the phrase that sums up this equation. Space-time tells matter how to move, and matter tells space-time how to curve. Okay, so the sort of basic idea of why we need a quantum theory of gravity is we know that from quantum field theory that the distribution of matter is quantized. It's a quantum object. We can have matter in quantum superpositions, and we can also have fluctuations in the number of particles existing itself. That really means that at some level, space-time also has to be quantum. So the question is how we go about doing this, how we put this all together. So that's essentially what we mean by quantum theory of gravity. Yeah, so it just means that space-time becomes quantum valued. The reason why this is interesting is maybe it might shed light on dark matter, dark energy, and also there's been some speculation that it might help us resolve the quantum measurement problem. There's a lot of theoretical difficulties. I am by no means an expert on this. I have no claims to being able to put forward a particular theory of quantum gravity, but the main difficulty seems to be that the theory is non-renormalizable. So all our standard tricks for creating a quantum field theory just sort of break down when we try and get sensible answers. There's also experimental difficulties, which is the effects of quantum gravity predicted to only become important on energy scales much higher than we could ever achieve in a lab-based experiment. This has led some people to speculate or maybe hope that that gravity doesn't behave like that. So this is what we call semi-classical gravity. This is where we force space-time to remain classical. So we don't have to modify GR at all. We don't need to deal with a quantum theory of space-time. But the expense of that is we need to somehow make the right-hand side of this equation classical valued. So one way to do that, for example, is to take the expectation value of the stress energy tensor. Of course, what that would mean is now quantum mechanics becomes nonlinear. So maybe the idea is that quantum mechanics breaks down at large scales and we no longer have these superposition states, and we always have classical valued classical valued energy density on scales large enough to influence space-time. this would require modifications to quantum mechanics, as I said, because it would mean that our quantum mechanics becomes nonlinear now. Okay, so pictorially, I like to represent it this way. I have here a red mass, which I'm going to refer to as a source mass, and the blue pendulum here I think of as a test mass, and the test mass is attracted to the source mass. So the question of quantum gravity at some level is what happens if I put my source mass in a superposition of two locations? Well, in a theory of quantum gravity, we expect our test mass to become entangled with that and also go into a superposition of two locations. So if you think about that, that really requires a quantum valued gravitational field and therefore a quantum valued metric tensor. Okay, in a semi-classical theory though, maybe somehow even when we put our source mass in a superposition, our test mass just sees a single valued gravitational field and just stays unentangled like that. So this is semi-classical gravity, where the gravitational field remains classical, or maybe there's some sort of gravitational induced wave function collapse or modified quantum mechanics. So maybe the presence of having a large gravitational field in a superposition, or maybe the interaction with the other mass somehow causes the state of the source mass to collapse, forcing the gravitational field to remain single valued. So both of these non-quantum theories of gravity would require modifications to quantum mechanics. Oh, I should also just say at any point, if anyone wants to ask a question, please feel free to interrupt rather than asking at the end if you want. So we can really summarize these sort of two approaches to the theory of quantum gravity is really hard and we can't quite figure it out. Semi-classical gravity is a little bit easier to figure out, but would require a modification to quantum mechanics. And currently we have no experimental data to distinguish between these two theories. And since one of them requires a modification to quantum mechanics, this seems like quite an important question.
Simon, if I may ask,
Yeah.
I could really appreciate that. Why would you say that semi-classical gravity would require modifications to quantum mechanics in general? This argument I couldn't follow.
Okay, I'll go back to this equation. Once you have equations of motion, like say, for example, this idea here would essentially lead to something like the Schrodinger-Newton equation, which I won't write down, but you have dynamics of your state that depend on the probability distribution of the state, because it's not just interactions within the Hilbert space, it's to do with, it's an expectation value, so it depends on the whole Hilbert space now. So you essentially get nonlinear equations of motion for your wave functions. And that extends to other things when we look at bigger Hilbert spaces as well. So the principle of superposition now breaks down once we start putting expectation values in our equations of motion.
So I can give you a counterexample. So in
Okay.
LHC, we run, everything in LHC is based on quantum field theory. Quantum field theory is based on quantum mechanics. And
yes,
exactly your same argument would lead to perhaps breakdown of quantum mechanics, some level, the linearity of quantum mechanics, or the breakdown of quantum field theory. And we don't see that.
Why? Why do you say this?
Because you're arguing that at some point your quantum mechanics, it has to be modified. By the same token, then I can also argue that my quantum field theory has to be modified. Quantum field theory, the standard model of particle physics has to be modified in some way or other. But that doesn't happen.
Sorry, are you talking about in particular something where we're forcing a quantum superposition to give a classical valued parameter, or are you just talking about the principle of modifying?
It is not necessarily that quantum mechanics has to be modified. You can always do the expectation value, and of course there are various other issues.
Okay, no, I see what you're saying. So you're saying that maybe we only see these effects in very high energy cases or whatever. I guess what the whole point of this game is to come up with an experiment that would show that. So for example, if we can come up with one experiment that shows gravity not behaving as you'd expect from a quantum theory of gravity, then we now have that experiment not obeying the laws of quantum mechanics, and we would have to modify it. So, finding one counterexample means that we've got a breakdown of quantum mechanics, I guess.
I'm saying that no, you don't need to break down the quantum mechanics. That's what I'm saying.
Okay, I guess I'm taking quantum mechanics in a much broader sense of all quantum theories that are all, including quantum field theory and the fact that it's linear. And I think that's true of all, relativistic quantum field theory. Once we change that, we have to change a lot of our theories.
Okay, we can.
Yeah, I'll move on. But it's an interesting point. And I think I'm hopefully going to address that later. Okay, so can we probe the details of a quantum theory of gravity in a simple experiment? So that is, can we investigate the nature of gravitons, which would be the quanta of space-time, essentially? So in principle, yes. I mean, if the theory is interesting at all, then it will have testable consequences. In practice, almost certainly not. And that's because the energy scales for observing and creating gravitons are just too large. However, we can look at an effective theory of quantum gravity, which is actually reasonably well understood. So in the linearized limit of GR, or the weak gravity limit, where we treat a perturbation to flat space-time and we quantize that, we actually understand reasonably well how this thing should behave. Can we test gravitation if the gravitational field is quantum valued in a lab-based experiment? So in principle, yes, and in practice, potentially. I think here's a good time to raise an important point. So you'd probably see an analogy here with electromagnetism. So a lot of the experiments that we talk about for testing if the gravitational field is quantum valued are a little bit analogous to saying that can we use the electromagnetic field to entangle two charges? And of course, we wouldn't, historically, we haven't thought of that as evidence that the electromagnetic field is quantum valued. What we've thought of is the presence of photons or observing shot noise and these sorts of things as, or observing spontaneous emission as evidence that the electromagnetic field is quantized. So what I should say is that these experiments aren't really going to tell us anything about the nature of gravitons or the quanta of the gravitational field. But what we can do is test the possibility of modified quantum mechanics due to the interactions of gravity in a lab-based experiment. Okay, so about 4 years ago now, these thought experiments were published by Segato and also one by Malato and Badral, where the basic idea is you take two sort of microscopic glass spheres that are entangled with a spin and put these in a superposition of two locations. The gravitational interaction will cause entanglement between these things. And because that entanglement relies on the fact that we have, we'll only get entanglement if this particle here sees a superposition of the gravitational field coming from this other particle, we take this as evidence that the gravitational field must be quantum valued. Okay, so basically it relies on the idea that only a quantum channel can create or can generate entanglement through some interaction via a classical channel where the gravitational field is single valued, cannot create this entanglement. So basically measuring, yeah.
Simon, I mean, because in your previous slide, you mentioned that you cannot test graviton hypothesis.
Well,
and I think maybe one should be a bit careful because this is the only, at least in the perturbative quantum gravity, this is the only way you can interact. And there's no other way. So in principle, you should be able to indirectly detect the nature of graviton If you change the properties of a graviton, you will get different kinds of entanglement. And if you
no, I
keep
take your point.
Yeah.
I'm actually going off some fairly broad statements I've read without fully understanding, saying that the effects of quantum gravity are expected to become important on very, very large energy scales. I guess that's more what I'm thinking of. That's more what I mean.
Actually,
you're right.
It's not because it's it's a long range. It's the same as electromagnetism. 1/r potential is there even at a very large infinity. So even there, you can talk about how the two particles are exchanging, photon or similarly graviton. And one can even locate what are the degrees of freedom of the graviton which are involved in entangling the masses and all. So in principle, you can indirectly test graviton.
Yeah, I guess what we need to do, I guess the other statements I've heard, if you're just testing it in the Newtonian regime, okay, we can say gravitons give us this residual force that looks like the Newtonian regime, but it's not telling us anything about it. And in particular, it's not telling us that those gravitons exist. The alternate theory is that you could just have a classical theory of gravity that obeys, Newton's laws of gravity or just general relativity.
And you have contradicted yourself. A classical theory will never entangle. So it has to be quantum.
Yes.
So if it has to be quantum, then the question is, what are the degrees of freedom are responsible for quantizing it?
I guess that's kind of my point. I guess I guess I'm viewing this as an indirect evidence of gravitons, rather than seeing a click on a detector. Like I guess, do you view the fact that an electron is bound to a proton as evidence of photons? I mean, you could argue that it is, but you could also argue that it isn't.
So that's why I said it's an indirect, but it is the only way. Even I see Higgs through this channel. I don't see Higgs popping up in LHC. I see Higgs decaying into something, say 4 fermions or 4 leptons, for instance. But Higgs is a kind of like intermediate particle, and this is the way even in LHC I infer the properties of Higgs mass, and Higgs everything about the Higgs properties. So in the same sense, nobody is going to see the graviton, but you will see indirectly. So all the particle physics which we know, they are always being seen.
No, I take your point. I take your point, and I think we're actually kind of agreeing. I guess I'm talking about something more explicit when I talk about, say, a direct evidence of gravitons. Yeah. So I think we're roughly agreeing. Okay, and this was, for me, this was a really interesting idea. This idea of entangling two microscopic masses through the gravitational field and using this to test the nature of gravity. Is it quantum or is it classical? I guess because this gravitational interaction is very weak, in order to be really sure of this, we need to build up a lot of statistics, and repeatability will be crucial. So it got me thinking about how difficult this would be, and maybe there's an easier way to do this. Okay, so at this point, I'm just going to give you a brief interlude. So a little bit about me for context. These are my abilities. I have zero expertise in general relativity, zero expertise in relativistic quantum field theory, and zero expertise in high energy physics. This should be a meta answer to the rest of Anupam's questions, which is I possibly don't know. Okay, my background is in quantum metrology, and in particular atom interferometry and entanglement enhanced sensing. So as I said before, when all you have is a hammer, you tend to see everything as a nail. So I thought maybe there's something we can do with atom interferometry to tell us something about the nature of quantum gravity. So just very briefly, a little bit about atom interferometry. The basic idea is you take an atom and split its wave function such that it travels along two paths. So we use optical transitions to do this with lasers that we can lock to atomic transitions, so they have a very specific wavelength. And it turns out that the phase difference that accumulates between those two components of the atom's wave function is proportional to the gravitational field, the effective wave vector of these atomic beam splitters, if you like, and the time between the pulses. Okay, so the reason why this is useful is that the effective wave vector just depends on the wavelength, which is locked to some atomic transition. The timing between the pulses we can control very well with a function generator, which is also ultimately locked to, say, some frequency standard or an atomic clock, so locked to an atomic transition, which means that this constant of proportionality depends only on fundamental constants of the universe. Or another way of saying that is there's precisely no calibration drift, or at least very, very small calibration drift. This means that atom interferometers are very precise and also very accurate, very low drift, and we can get more and more precise just by repeating the experiment many times and building up statistics. Basically, all these three things are the same way of saying the same thing, which is there's no drift, which is allows us to make a very precise calibration-free measurement of the gravitational field.
Simon, could I just ask, what's the physical mechanism? How does the gravitational field impart a phase on the atomic?
It's really, there's a couple of different ways of understanding it, but the simplest way is really just that if you view it in the frame of the atoms, they fall and, oh sorry, if we view it in the lab frame, the atoms fall and you can see that the laser beam has a phase that varies along the z-axis due to the wavelength of light, and how far the atoms fall depends on gravity. So it's really just the atoms in free fall. You're measuring how far the atoms dropped very, very, very precisely.
Okay, cool.
Yeah. This is just an example of what an atom interferometer looks like. In particular, this is the one in the lab at ANU. It's about 3 meters long. The atoms drop down this vacuum tube. Here is the first floor of the building, and they cut a hole in the floor to put this thing in so they could make the atoms fall longer. And we use this to measure G. So what I mean by that is we use it to measure the acceleration due to the gravitational field. So what is G in SI units? I'm sure this is one of those constants most people have stored in the back of their mind, about 9.8 meters per second. On a particular day in 2018, one afternoon, they did this measurement with the atom interferometer and they found this. Okay, so let's have a look at the information that's hidden in some of these decimal places. So the latitude of the Earth is in here at about the second decimal place. So Canberra is at a reasonable, it's reasonably close to the equator. So, and the Earth is a bit oblate. So that reduces G a little bit. We're also at about 500 meters. The density of what's directly under the lab matters. So if there's, say, sandstone instead of granite, that shows up in these sort of decimal places here. Where the moon is directly overhead and its influence on the tidal forces will change things. If people come into the lab, like a stupid theorist comes in and starts asking annoying questions about how atom interferometry works, that starts to change this digit over here. And then hydrology. So if it's been raining a lot, the water seeps into the ground and affects these last couple of digits down here. So we really can make very, very precise measurements of gravity with atom interferometers. And this has been put to good use in science. So it's been used to refine our measurement of big G. It's also been used to improve our measurements of the fine structure constant. Just recently, it's been used to define the kilogram instead of fundamental constants rather than a lump of platinum in Paris. In the future, we're hoping, well, there's hopes to use it to test the weak equivalence principle, maybe gravitational wave detection, and as I'll get to in a minute, probing the quantum nature of gravity. Okay, so this was my thinking. So in 2017, I saw that paper by Segato and also the one by Marletto and Vedral. And not long after, in 2018, I started thinking to myself, if atoms can be used to measure classical gravity very precisely, maybe they can tell us something about quantum gravity. So how can we do this? Okay, well, let's look at space-time curvature from a collection of quantum particles. So again,
Sorry, before going to the next step, is there really any experiment that has detected the effect of classical gravity in the experiment that you explained? Because this would be the first step.
We can certainly measure classical gravity. Like we can measure little g to 10 decimal places.
With a quantum system? With a quantum system?
Definitely. I mean, this is a quantum system. There has been, so here that each atom is in a superposition of two locations. There's also been measure of the curvature of the gravitational field, if you don't like just measuring a uniform gravitational field. So essentially, gravitational gradient is curvature of the gravitational field. What else was I going to say about this? Yeah, also big G. So not just gravity from the Earth, but the way we measure big G, Newton's constant, well, not me, but the way other people do it, is they essentially take a bunch of really large masses, maybe 100 kilograms of lead weights, and put them next to the device and calibrate that really carefully and measure the change in the gravitational field from that.
Yeah, but they are not quantum systems. Huh? When you get too big mass,
I see what you're
not
saying.
a quantum system.
Yeah, I see. So you want to see a gravitational interaction
really,
between
yes,
two quantum systems.
In a quantum, for instance, gas, as you explained, something like that.
No, we haven't, and that's kind of exactly the point. So that you're right. That would be the first step, and that's essentially what I want to talk about.
Okay, thank you.
Yeah. Okay, so in linearized gravity, you can show without too much drama that the perturbation to the metric tensor is just, we can just use the Green's function solution, and we see that it's proportional to the distribution of our matter. Here n is the number density operator. Of course, if our matter has got a quantum distribution, then this kind of has to be quantum valued. Or another way of looking at it is we get a quantum valued gravitational potential. Special thanks to Zane and Joe.
Simon, I think one has to be a bit more careful here. It's just because the mass is quantum doesn't mean that my graviton H00 is quantum. So one has to ask what are the degrees of freedom you're quantizing, what is H00? Otherwise it doesn't make any sense, perhaps.
Yeah. Yes, there are some papers that go into this that probably are a little bit beyond my depth to recall at the moment. Perhaps we can talk about that a little bit more after. But yeah, this is something that people have debated about. Okay, let's look at the Hamiltonian for particles interacting via a gravitational field. Okay, if we look at the gravitational self-interaction, of course, we've got this integral over r and r prime, and we have to consider our matter distributions at r and r prime. Or if you think about it, it's the interaction of our matter distribution with our quantum valued gravitational potential, if you like. And I'm arguing that this implies a quantum valued gravitational field or quantum valued metric. If, however, we force the gravitational field to remain classical valued, okay, we can still have a quantum valued Hamiltonian. That means our energy can still be in a superposition state, but that's really only due to the distribution of our test masses, because our gravitational potential remains classical valued. So it's sort of saying, although we have a symmetry between source masses and test masses, we're sort of saying that all our source masses somehow add up to give a classical valued gravitational field. And then our test masses are quantum valued and you can go and sample that field. Okay, the important point being that this has 2 powers of the number density operator in it, and this has only 1 power of the number density operator in it. Okay, so the basic idea for the experiment would look something like this. I'd take a dilute cloud of ultracold atoms, do some state preparation, which would include splitting them into 2 components, but maybe in that I'll include some kind of entangling step to give me freedom in the quantum state that I'll produce. I let them interact gravitationally for a while. So the red atoms the atoms in this red path only interact with themselves, and the atoms in this blue path only interact with themselves, and they're far enough away that I can ignore the cross interaction. I would then bring them back together again and do some interference type experiment, and then I would perform some measurement. Okay, and as I argued before, if I'm allowing for the possibility of the gravitational field to be quantum valued, which allows me to have entangling type operations happening, my Hamiltonian will be proportional to JZ squared. Here, JZ is the number difference operator for people who aren't familiar with that notation. But if my gravitational field remains classical, at most my Hamiltonian can be proportional to JZ. So my exercise now becomes an exercise in, can I do an experiment that will determine the difference between these 2 possibilities? Can I resolve this in an experiment?
Sorry, Simon, can you, I didn't get that argument. I guess I feel like if I have so I guess if you, what is that argument based on? Because I guess we have some kind of theories of classical gravity, and we get effectively the same behavior, that it goes quadratic in the energy. So I'm just wondering why you.
Okay, so this comes down to this
quantumness rather than, yeah.
Okay, this comes down to the idea that in order to get this entanglement happening, in order to get, I guess, one particle seeing, when one particle is influenced gravitationally by another particle in superposition state, in order to become entangled with that, it's happening through the gravitational field, and it can only happen if that gravitational field is also in a superposition state. If that gravitational field is classically valued, one particle only sees a single value and doesn't go into a superposition state. So this is the argument that Sagato made in his paper in 2017, essentially saying that only a quantum channel can cause entanglement.
Well, that I would totally agree with. But I guess here you're looking at an interaction Hamiltonian, and in the interaction Hamiltonian, if the gravitational field, so there it's basically like the, in GR that would be the metric coupled to the mass, so it would just be just the metric Hamiltonian, and if the source of that classical field is other classical objects, like say for example, is other masses, then you would expect exactly that same type of interaction. No?
If the source of the gravitational field is other classical masses, we can't have this. This, for example, would be a classical valued density, say without a hat on it.
That's right. Sorry,
yeah,
so I'm having to. Okay.
Can you see my mouse?
Yeah.
Yeah. So if our source masses were classically valued, okay, then this would be just a number rather than an operator. So it would be classical valued, and our Hamiltonian is still quantum valued, but only 1 power of the density operator, rather than 2 powers of the number density operator.
Great. Why only 1? So I guess if you compare it to say these like stochastic theories of gravity, then we would have, for example, that the first mass is a stochastic. So it's the actual mass plus some stochastic terms, and the second mass is the mass of the, I guess so one you treat one as the source of the gravitational potential, is the actual field, and they're both just different objects. Why is the fact that one is quantum versus, whether the fact that they're quantum or classical?
Okay, so
example, in a completely classical theory of gravity, you would expect to have both terms there, right?
Yes, that's correct.
So in a completely classical theory of gravity, it's also quadratic in the mass.
Yeah, it's fine that it's quadratic in the mass. What I'm saying is that in order to have this quantum-quantum interaction, the thing that mediates that interaction between them must also be quantum valued.
That's right, but that shouldn't. Yeah. So I totally agree with that, but that shouldn't change the fact that it seemed that you were making a point of whether it's quadratic in the mass or linear in the mass.
Oh, sorry, it's quadratic in quantum operators.
Okay,
not that
good.
It's quadratic in the density. Sorry, it's quadratic. It's got two powers of quantum operators in it, rather than just one power of a quantum operator. That's my point.
Okay, thank you.
Okay, cool. Sorry about that.
Yeah.
Okay, so this is our experiment. We're trying to distinguish a Hamiltonian that is mediated by a quantum value gravitational field, which I argue leads to a JZ squared type Hamiltonian, and one where the gravitational field that mediates the interaction has to remain classical, and this can at most be proportional to JZ. Okay.
So that's where I guess that's an assumption. That seems to be an assumption there about so if it was a purely classical spin, then you would have that it was proportional to J squared being a quantum operator. If it were in the complete classical limit, it would be that proportional to, again, J squared, but J squared being now a classical spin.
Yeah, that's the important point, is I'm always talking about multiple powers of quantum operators. Right. Yeah.
But I guess,
and that's the thing we're trying to distinguish.
Okay.
But I'm also a bit lost, Simon, here. I mean, why would you say that it is it's only proportional to JZ and not JZ squared? This I didn't understand actually.
Okay, it comes basically comes from this argument, and I know this is a bit fast and loose writing it this way, but there are other papers that argue via basically causality arguments that in order for gravity to not act like an action at a distance.
By the way, Newtonian gravity has no causality. Newton didn't know about causality. Newton didn't know the speed of light.
Yeah, of course, but we do. Yeah, we know
I don't
about the speed of light.
understand this argument.
Okay. Do you agree that gravitational interaction between two objects has to be mediated by something in between them?
Okay, yeah.
Yes. Okay, and that's basically, that comes down to causality, that needs to be true. If we have entanglement being generated between these objects, okay, this object doesn't see this object, right? What it sees is the field that mediates them. That entanglement can only happen if that field is quantum valued, because this object doesn't directly become entangled with the other object, it comes entangled with the field. So that field being quantum valued is the important step.
There is a subtle difference. It's the off shell, not the on shell. It's not the gravity hits something like this. It's completely an off shell process. And that is something which perhaps is the difference which you are talking and maybe I'm.
Yeah, okay. Again, I've heard this argument and I've read the papers that.
No, you don't have to heard the argument. You just have to open some books on quantum mechanics or quantum field theory.
No, sorry. I understand that it's on shell rather than off shell.
But Simon, which paper are you attributing to that argument? I guess you seem to be jumping from the statement that if it's quantum, it is attracted to the mass as an operator, to then the statement that if it is classical, it's attracted to, and then you're kind of omitting what it would be. You're kind of omitting to what the source would be. And I think for that, it might depend on what you mean by semi-classical gravity, or what your theory of gravity is. And I mean, there's certainly theories of classical gravity which aren't based on the semi-classical equations, which don't give you such a behavior.
Yeah, I agree with that. There are theories of semi-classical gravity, but
well, I don't want to use it. I didn't say semi-classical gravity because I guess I attribute I feel like what your argument here is based on the semi-classical equations, where because it's attracted to the expectation value, you see kind of this weird behavior, and I would reject.
Yeah, so it's actually not just limiting itself to that class of theory. It's not just the expectation value. This is ruling out all theories where the metric remains classical valued.
Okay.
Yeah, that's what I'm trying to argue.
Can you point to a reference where that is?
I can. Maybe I'll try and post. I mean, I don't have them in my head, but I'll post them. I'll send an email later with some other references. Yeah.
Okay. Great. Thanks.
Yes. Cool. Thank you. Okay. Okay. This is a point I wanted to make because of a paper where I saw this argument discussed, but I think maybe in the interest of brevity, I might skip it. Yeah, I think I'll just skip this. Just wanted to clarify a misconception in the field. I think this is perhaps the wrong audience for this one. Okay. So I guess now it's time to use my powers, which is quantum metrology, to try and resolve this question. So my argument is, again, that quantum valued gravitational interaction leads to some evolution that looks like this, whereas classical valued interaction can lead to some interaction linear in JZ. So unlike previous approaches, I decided to try and use some of the tools from quantum metrology to address this. So I introduced the Fisher covariance matrix. I'll explain what this is in a minute, but basically it's a measure of how rapidly the state changes proportional to these different parameters. Okay, so in particular, the diagonal term here tells us how rapidly the state changes with proportional to this parameter lambda q, which is something that parameterizes the strength of the hypothetical quantum valued gravitational interaction. So really our exercise is to perform some experiment that can resolve this. Well, basically can resolve that lambda q is not 0. Okay, so what is lambda q? Well, in terms of our parameters, it depends on the mass of our particles, our interaction time, and sigma is a parameter of how tightly we confine the system. M is the number of repetitions, and FQ is our Fisher information, which is going to be some function of the total number of particles we use in our experiment. So the question is, what is the state that maximizes FQQ? Okay, so it's quite a non-classical state that's reasonably difficult to manufacture. It's actually not quite a Schrodinger cat state. It's a superposition of a symmetric Dicke state and a Schrodinger cat state. So what that looks like on the block sphere is this. So it's a superposition of all our atoms in one arm of the device, all our atoms in the other arm of device, and an equal split. So that's this is the superposition in one arm or the other arm, and this is our 50-50 superposition. So each atom is, sorry, we have exactly the same number of atoms in each arm. So it makes sense why this is the state that would maximize our sensitivity to this effect, because really it's the state that maximizes the quantum fluctuations in the gravitational interaction energy. Because when all our atoms are in one mode, for example, our gravitational interaction energy is high, and when our atoms are evenly distributed, that's when our gravitational interaction is minimized.
Simon,
okay.
Sorry,
Yeah.
Can you ask you a question? So wouldn't a single n by 2 also, I mean, if you're looking at the difference between Jz square acting on this and Jz acting on this, right? I guess you would also find a difference between just 0 z and n/2 z, right? Or
yes, you would.
Or even the latter, just the second part, right, would give you some difference on that.
No, this part will not.
You know,
this
square
part
will
will
not
give
give
a difference, but it won't result. It won't tell you that.
it will be outside, right? You want to relate, right? Yeah.
Yeah. So it might help you measure the classical interaction or the value of that, but it won't tell you what the quantum one is. Yeah. Okay, so for that, our Fisher information is proportional to n to the fourth, which is great. I'll come back to some scaling arguments with that later. Cool. How do we make this state? We don't know. So this is a sort of state that a theorist like me likes to dream up, but if I can't come up with a recipe to go and tell an experimentalist how to make this state. Okay, but there's another state which we can make, well, sorry, that I know how to make. And it's reasonably straightforward. I take a coherent spin state, which is the state that you get when you just take an ensemble of atoms and put each atom into a superposition state. This is the operation we do all the time when we do atom interferometry. Then I can apply a nonlinear interaction to this state. So this is just to prepare my initial state. The way we can do that is via a one-axis twisting technique. We can do that with a controllable system using cavity-induced one-axis twisting. So we essentially put our atoms in an optical cavity, turn on our electromagnetic field to create our special entangled state, and then turn it off again once we've created the state that we want. And then we separate it and look for our gravitational interaction. What that state looks like on a block sphere is sort of this. It's sort of a superposition of 4 separate blobs. This is certainly, while I know the recipe to make this state, it's certainly beyond our current experimental capabilities. People have certainly done this cavity-induced one-axis twisting technique, but certainly not to the degree to make states that look like this. They can make squeeze states and non-Gaussian entangled states, but certainly not these sorts of spin cat states yet.
Simon, if I may ask you, so besides gravity, you will also have a photon interaction, so which will so atom-atom interaction, and they would be probably much stronger than and given the fact that even here the density is not so as good as what we proposed in the case of diamond, because you're taking a cold neutron which is weakly it's not very dense essentially. So what happens to that? I mean, won't that electromagnetic interaction would overcome all your
yes, I'll get to that in a minute. So I think essentially that will be that is essentially the main problem. There are techniques to address it, which I'll go into a little bit. So maybe I'll get to that now. I'll come back to these. Okay, so a gravitational interaction essentially will have the same form. Okay, and that's for the same reason. And with our techniques of controlling atomic interactions, so they're neutral atoms. So it's essentially the van der Waals force. So essentially that drops off much more quickly than gravity, but of course it is much, much stronger. But crucially, it depends on how the atoms are confined in a different way. So if sigma is sort of the size of my confinement, maybe I just pretend it's a sphere for the moment, so I only need one parameter to confine its size. The strength of the gravitational interaction goes as sigma to the -1, but the strength of my electromagnetic interaction ends up going as sigma 1 on sigma cubed. So of course, that means as we expand it, our gravitational interaction drops off more slowly than our electromagnetic interaction. We're probably still never going to get to the point where the gravitational interaction overtakes the electromagnetic one. But because of this different scaling, by varying that parameter, you can kind of separate the effects of the two. Okay, if you've got these two parameters in your Hamiltonian, varying the scale, varying the size or the confinement of these things means you can separate out, okay, this contribution was from my electromagnetic interaction, this contribution was from my gravitational interaction. The other thing we have is, for some species of atoms, Feshbach resonances, which we can use to control and make the atomic interactions very, very weak. But no one has demonstrated the kind of control that we would need at this point. Yeah. Okay.
So Simon, hi. So if I understand correctly, it is very similar to the kind of staying far away that kind of from Casimir force in terms of, so each pair of atoms have to stay far away from their van der Waals, right?
Yeah, for exactly the same reason.
Yeah, but in the case of two masses, you have the chance of putting a screen actively also, which I guess, well, the Feshbach is probably your analogy there, but it's a tougher one. Yeah, I see. Mm-hmm.
Yeah. Okay, I'll jump around a little bit, but let me get to this. Okay, so it's not just enough to resolve this term. Okay, so the off-diagonal terms of the Fisher covariance matrix basically tell you how distinguishable are the two different effects from each other. So it's no point saying we can resolve the effect of quantum gravity if it turns out that if the effect we're seeing, we're not sure if it's from quantum gravity or from classical gravity. So it turns out for the optimal states considered here, these off-diagonal terms are zero, which means that they're entirely distinguishable. So what I mean by that is, here is the probability distribution from our measurement outcomes. So the idea is I would take my initial state, prepare my entangled state, let them interact via gravity for a little bit, bring them back together, and basically do the reverse operation that I did here. And if there was no interaction at all, I would end up perfectly back in the same state that I started with. So that would be all my atoms in the blue mode, for example. If we have this quantum gravitational interaction, what we see is a little bit of transfer of probability to this measurement result over here. However, if we have our classical gravitational interaction, we see an entirely different change in our probability distribution. So this is what I mean by the two results give entirely distinguishable, differentiable effects. We also considered two different classes of gravity causing decoherence, and they also have distinguishable effects from our quantum gravity. Okay, I'll just finish up.
Sorry, just
I'll
a
start
question here.
Yeah.
Is there the difference that you showed in the previous slide, the difference between a quantum gravity effect and a classical gravity effect? Does it depend on the nature of, for instance, type of quantum intermediate for gravity? By this, I mean, for instance, if the gravity is spin 2 or spin 1, or I don't know, spin 0, something like that. Is there any
details of that I'm not sure about, but what we do know is that all of those things must yield the same behavior in the low energy limit, in the Newtonian limit, right? So what I'm basically showing is, if we have the quantum version of the Newtonian force, this is what we would have. I guess the only real thing that a different properties of different versions of quantum gravity can do is affect the strength of this interaction. But again, we wish to recover the Newtonian limit when we knock the hats off everything. So that kind of constrains the prefactors in the theory.
Okay, thank you.
Yeah. Okay. So basically what I want to talk about is the benefits of my approach to looking at this. So what I want to, in particular, what I mean by my approach is what distinguishes the way I've looked at these things from some of these other experiments that try and rule out gravity as a classical channel. So experiments with, say, glass spheres or micromechanical oscillators, and also using a quantum parameter estimation approach. So quantum parameter estimation gives us some really useful tools. So straight away, we can maximize the detectability of our system, the detectability of these effects. Think tools like the Fisher information tell us things like what state preparation should we do to maximize the size of the effect, or what parameters should we tweak in our experiment? And also importantly, how can we use this to maximally distinguish, say, quantum gravity from other nuisance parameters, like, say, classical gravity or some other thing that could be causing a similar effect. The other approach that I've done, which is a little bit different to what other people have looked at, is using atoms, so many microscopic particles rather than a few mesoscopic particles. As we can see, it gives us an enormous freedom in our choice of quantum state, which allows us some useful things like making states that are entirely, where the effect of quantum gravity and classical gravity are entirely orthogonal, essentially. The other useful thing I'd like to point out is that the sensitivity of this thing improves rapidly with the number of atoms. Essentially, that's because we get a larger effect, because more atoms mean more mass, but we also have a much improved ability to measure that effect, because the more atoms we have, the more precisely we can measure a gravitational field. So you start to see that at scales, as you increase the number of atoms in the system, it really rapidly improves how resolvable effects of quantum gravity are. The other thing I'd like to say is atoms are free from drift, so we can build up statistics over many repetitions. So that kind of gives us a lot of advantages there. Let me go to the next slide. Okay, so is this possible? At the moment, I would say no. Okay, so we would need to create 10 to the 8 atoms, which we know how to do. We can make Bose-Einstein condensates with 10 to the 8 atoms. What we can't do is make these highly entangled states with that number of atoms. Okay, it just becomes very difficult. So where I got that number from was assuming 1 second of interrogation time, which is about how long we drop our atoms for in our atom interferometer at ANU, and a day of interrogation time. Okay.
Sorry, again, a question here. I heard recently there has been possibility to make a condensate with 2 different energies, sort of superposition. I don't know if can it help? You have 2 condensate of 10 to 8 or something atoms, and they are splitted in energy, therefore, and probably positions also.
Yeah, we can certainly do that. When we do an atom interferometer, for example, that involves putting atoms in superpositions of different electronic states, and those electronic states have different energies. I guess the way that would come in to some experiment like this is looking at the different mass energy in those things. And I'm guessing that's probably too small to have any effect compared to just the rest mass of the atoms all interacting with each other. Yeah, it's something I haven't thought about, to be honest. So yeah, that's a good question. And I'll think about it a little bit more.
Okay, thanks.
Okay, the biggest problem, which of course Sagado picked up right away, is that we need orders of magnitude better control of the atomic interactions. So while this sort of first step, I think, is if we try really hard, something that we'll probably achieve in the next maybe 5 years, I think we will be, the way the field is advancing at the moment, I think we will be making very large condensates in highly entangled states, or even just dilute gases. They don't even have to be Bose condensed in highly entangled states. However, it's this residual atomic interactions, electromagnetic interactions, which are probably really going to be the killer. Yeah, but as I said, maybe if you can't get rid of them, you can separate out which ones are the electromagnetic interactions and which ones are the gravitational interactions, just by varying the size and seeing, you know, how these effects go up and down. Okay, so I'll at this point wrap up. So I think, as everyone's identified here, testing quantum gravity with ultracold atoms probably sounds a little bit crazy. It's just a little bit too difficult. In particular, I'd say it's about as crazy as detecting gravitational waves sounded 40 years ago. So, you know, maybe it's something, if we considered it worthwhile and we thought about really hard how to do it, it's something we could maybe do. Probably much less crazy than looking for high energy gravitational effects in the lab. And I'll finish on that point. Thank you, everyone.
Thank you. Yeah. Thank you very much, Simon, for a very interesting talk.
Thanks.
I guess just to kick off questions, I'm not sure if other people have one. I guess a lot of questions have been asked as we're going. I was just wondering if you can give us some sort of estimate. So you've mentioned that sort of the two big hurdles to achieving this sort of experiment are getting the twisted off-axis state, or sorry, is that the TOA state, and then the other one is just controlling these the electromagnetic interaction. Or I was wondering if you can give us any sort of a idea. I know it's a bit of a how long's a piece of string, but any idea of how long you think it will be before we get to there? Are these like in the far future, or is it, you know?
Let me maybe tell you where we're at. Okay, so people can create spin squeeze states with atoms. So these are atoms, these are entangled states of many atoms. They can easily do that with 10 to the 7 and 10 to the 8 at the moment atoms. What we can't do is make these really, really highly entangled states, like states where we've got bimodal probability distributions. People have done that with things like 1,000 to 5,000 atoms, or actually up to 10,000 now. So they've made what I would call non-Gaussian squeeze states, which start to have things like bimodal probability distributions. So it's not quite a Schrodinger cat state or something, but that's done with small numbers of atoms, of course, via a different technique. So does that technique scale? Probably not. There's a whole bunch of things we need to do in between there, but it's advancing. Okay, the bigger problem being the residual electromagnetic interactions. I don't remember the exact numbers here. I think I calculated that we'd need, so you can control these via Feshbach resonance. The problem, which is basically using a magnetic field to alter the S-wave scattering length between the atoms. The states we're looking at are actually not particularly dense. When I looked at these, it scaled better. Letting the system be a little bit more dilute, you would really turn off the electromagnetic interaction a lot, but leave a fair bit of gravitational interaction. So it seemed like having a fairly dilute system was the way to go. That said, the electromagnetic interaction is still there. You control the S-wave scattering lengths with the magnetic field. So now it comes down to the question of magnetic field stability. If you calculate that, it looks like you need sort of 10,000 times better magnetic field stability than is currently demonstrated. So a lot, but you know,
not out necessarily. It's certainly not in the realm of impossibility.
Yeah.
All right, thank you. Jonathan, I think has a question.
Hi. Yeah, thanks for a great talk. I was just wondering, with the systems that you're looking at, or maybe other systems, kind of what precision. So you mentioned precision tests of gravity, and I was just wondering what precision you can get and over what time scale. So I guess we're interested in, for some experiments, we're interested in kind of how quickly you can measure the gravitational field and at what accuracy. Do you have any idea of what atom interferometers that you're thinking about?
Yeah, I'm going to be getting the numbers wrong. Okay, so per shot sensitivity. So a shot of a device takes about 1 second, maybe a bit less. we're looking at, say, 1 part in 10 to the 8 on the gravitational field. And then you can go down lower by, you know, integrating your doing many shots of your experiment, because you've got 1 over square root m shot noise on that.
And 10 to the minus 8 is a relative uncertainty. You mean a relative uncertainty?
Yeah, in little g. Yeah,
right.
From a single shot.
Thank you.
Yeah.
And that's with the exact devices that you were shipping.
Yeah, and this is without using quantum entanglement or anything. This is just using uncorrelated atoms, dropping them through an atom interferometer device. Yeah.
Yeah. Thanks.
So Simon, can I could just ask a bit more clarification on that, because even for the single atom interferometer, single B coming from a BEC, still 1 by root n of the cloud that you're using per run, right? So 1 in 10 to the power 8. I mean, I can see people have done that. So maybe 1 in 10 to the power 8 would still mean 10 to the power 16 atoms having.
No. So 1 over square root n. That's So you've got power of 10 to the minus 3 for the number of atoms. But then we have a prefactor. Remember?
Right.
Yeah.
Of course.
So this number here in particular in SI units is about 10 to the 7.
Yes.
And T will set it to be about 1
second.
Yeah.
I see.
So we have a 1 over square root n.
Yeah. So per root hertz. Yeah, that's great. Because I understand that. So per root hertz.
Let me write this down.
Yeah. So the time that you take to do this is still a second, right, per run. So it per root hertz, the thing would be exactly like 10 to the power minus 8 per root hertz, right?
Something like that. So 1 over t pi squared. And maybe it's a little bit less than a second, depending on the drop. But we can also do a bit bigger than a second if you have a really big drop tower. And then that's the number of atoms in your device. And then if you repeat it many times,
exactly. Root n.
We'll stick in one of those. And it's unlikely that you get 1 second repetition, because you have to make your atoms again and drop them again. So maybe 10 seconds repetition. Yeah.
Right. So per integration time wise, so per root hertz, this sensor is not that fast. It's a slow sensor.
Yeah, very slow. Very slow.
Yeah.
What it's useful for is it's accurate, has no drift. So if you wanted to detect a fluctuating gravitational field, you'd use some mechanical device, like something on a cantilever. But the calibration on that thing's terrible. And really what you do when using one of those is you would periodically recalibrate it with your atom interferometer, basically.
Yeah.
Yeah, to stop the drift in the response of that thing.
No, that's true. I understand that. And looking still at this formula here, so so when you said these 2 modes, so you wanted a state where n will be in, or you wanted this JZ square operation to act, right, for a while to prepare your state also, right, which will be like a Kerr nonlinearity, well, given from electromagnetic interactions. I guess you want to prepare it fast enough.
Right? Yeah, but we want it in some way that we can control it and turn it on and off.
Right.
So that's why I went with, say, hang on, I'll just stop annotating my
Fishbach.
Yeah, we want it so that, hang on, annotate, cool. Maybe you can use an optically induced nonlinearity. So the way this works is basically you have a atomic optical coupling which alters the number of photons in the cavity, and then the number of photons in the cavity feeds back into the atomic energy levels, and you get a JZ squared like interaction. Yeah, and this has been demonstrated as a way to create one-axis twisting. And the great thing about it is you can turn it on and off and control it really easily.
Okay, if I may interrupt, I think it will perhaps the gravity-induced entanglement will be very, very tiny, because irrespective of whichever stream you choose, I think in our 2017 paper, we had already put down some numbers you would require a mass of the roughly of the order of 1 part in 10 raised to 14 to get a entanglement phase, which is roughly of the order of 1. So it's very hard to see that how could you boost, to get 10 raised to minus 14 kilogram mass, you would really need a huge, very dense condensate.
And I guess this is,
it boils down to the same as taking, either you play with a diamond or very condensed system. I think maybe it's better to then play with something which is very dense, highly dense system rather than BC.
Yes, however, I want to highlight an important difference here.
Sure.
While the logic is the same as creating gravitationally induced entanglement, because we know that the interaction of this form can lead to gravitationally induced entanglement, we're not actually looking for that. Okay, what we're doing is viewing this as a parameter estimation problem. We're looking for, is it distinguishable? So if this Hamiltonian is true, can we detect its presence? Okay, and although the entanglement phase won't be as large because we're using less mass, we have a lot of atoms, okay? And atoms we can use to very sensitively probe, essentially probe the gravitational field very precisely. So that's why it's a little bit different. It's not quite the same as just taking a glass ball and breaking it up into little chunks. There's sort of a little bit of a subtle difference there.
No, absolutely, I appreciate this subtle difference, but then you will have to make measurement in all the n atoms to make anything concrete.
Yes, absolutely, and that's difficult.
And I think this is impossible. It's impossible because you will have decoherence effects. Even, there's no guarantee that if I'm shining a small amount of photons on one atom, I will not destroy the coherence of the other atom.
Well, it comes down to,
highly infeasible technique, in my opinion.
It comes down to the same question of, can we produce these sorts of highly entangled states? And currently we can't, for the reasons you're saying, but we can start to produce fairly entangled states with a lot of atoms, or highly entangled states with a smaller number of atoms. So if you can do that, that is evidence that showing that you can produce these states is essentially the same as saying that I can detect these states well enough to measure the gravitational effect. Okay, if I can include the interaction time and rule out some of the other effects. So yes, it's very difficult, but I think we would have to read the literature a little bit more before we can rule it out completely, right? It's making entangled states is something that there are a lot of people making a lot of progress on at the moment.
I guess the susceptibility to loss, to atom loss, or not knowing the atom number precisely is have you looked at that?
I've looked at how loss affects it, and that essentially constrains how tightly you can close the system. I haven't actually done a proper calculation with decoherence due to three-body recombination, but yes, that would be something that you'd totally have to minimize.
But it is not an effect which depends on like plus minus one atom being added or subtracted. Would it make a big difference?
No. So there are some states where that would be an effect. I know the sort of things you mean, but you can produce a scheme where no, it doesn't quite give you that level of decoherence. Yeah.
I think Jonathan had his hand up again.
Yeah, so sorry, background noise. So do you have a way of increasing the precision without increasing the time, like to go from 10 to the -8 per second to something else per second?
I mean, you can, without increasing the time, you can increase the number of atoms, I guess, or no, not really. Yeah.
If you increase the number of atoms, how does the noise, I guess that also increases the noise, like how does your precision increase with the number of atoms? I guess if you're unentangled, I guess it depends what kind of states you're firing in, whether they're entangled or not.
Yeah. Okay. So the Fisher information, which is the thing that tells us how detectable it is, goes as the number of atoms to the fourth. Okay. But what it doesn't, what it won't help us with is the residual electromagnetic interactions, because they will also increase by that same amount. So, yeah.
Thanks.
I just had a thought myself, a question myself. I was wondering if, obviously, like given it's a single interferometer and comparing both to the first order, the background gravitational effects won't really hinder anything. Like they would amount to a constant phase, but if you got some sort of fluctuating background gravitational effects, the curvature in those, I guess, how would that affect it? Would that look like a stochastic noise term, or would that be, given it would still, this would be entirely a classical phase, so that would definitely have the sort of the signature of the phase, but if it's stochastic, would that be distinguishable still?
No, so if you've got a, say a fluctuating or even just classical but stochastic time-dependent gravitational field, I don't think that would be distinguishable. I think, okay, so that would be a classical term, so it would be like a JZ term, but
I guess it would have like a fluctuating lambda c in that case, and so whether
it's a good question actually. I initially assumed that no, it would ruin everything, but now I think about it a little bit more. I think maybe it might be okay as long as it's not too large, because I think you're right, it will have a different signature on your probability distribution. You still have to gather a lot of statistics to, faithfully reproduce that probability distribution, but the terms that would show up from a fluctuating classical gravitational field would actually be, I think, distinguishable.
Okay. And that would be true both for like some sort of external classical field, as well as if, your, say, semi-classical theory of stochastic gravity of an interaction is sort of, Maxwell's demon-esque trying to screw you, basically.
Yeah, to be honest, I don't know. That's a really good question. I have to think about that. Yeah.
Thank you. Just for whoever asked the question before, this will all be recorded. It should be online.
Maybe one last point, just wanted to make. I think because this, how big, Simon? So just could you, how big will be the, your cavity where you're preparing all these cold states? Just to give an idea roughly.
Yeah. Okay. So we're looking at confining them to, say, 50 or 100 microns, so 0.1 of a millimeter, and then separating them. I don't know, as long as it's large compared to that. So separate them by a millimeter, maybe do that in free fall, maybe do it via optical dipole trapping or something like that. Obviously, the less interactions and less external forces you have on your system, the better, because you want to eliminate those things. Yeah, this is really a schematic. We can certainly do schemes where we prepare a system, make an entangled state in a cavity, and then drop them. This reverse operation we'd have to think about a little bit, maybe. Yeah.
Thanks. Yeah.
If there's no further questions on that note, I think we should thank Simon again and let him go to sleep, since it's getting well and truly into the night. So yeah, thank you very much for a very interesting talk.
Thanks, everyone. That was fun.